Hi, welcome to the video, and the idea for today is that we take a look at the dimensionless perspective of settling velocities and also why this is important or necessary. So therefore we would first like to take a closer look at the drag equation, the equation you should already know from previous videos. And then we shortly introduce spray drying, really just one page about spray drying as an important example. And we will discuss how to consider different flow regimes for particle setting, which is basically the idea behind these dimensionless look. So the drag equation or the drag force of a sphere and the related equation should be familiar to you already. So drag force is the resistive force that acts opposite to the relative motion of an object through a fluid. So if a particle goes through air or water or another fluid, it will feel a drag against its motion, and this drag comes from the friction of the fluid. So the fluid has a friction on the surface, and there could be also a pressure difference, right, around the object, and also this will cause drag. And the general equation of drag force is shown here. So the density of the fluid divided by 2, and then this is the important part, this is the drag coefficient as a function of the Reynolds number, and here we have the cross-sectional area of the sphere and the velocity, the relative velocity between the particle and the fluid squared. And if you take a look at this equation, and we already solved it for different assumptions in previous videos, we see that this equation does not provide an explicit expression for the settling velocity as a function of particle size. Why? So if you want to reshape this equation as the particle size equals blah 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 as a function of velocity, or the velocity equals blah 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 as a function of particle size, this is not possible for the full equation because of this expression here, right? In Stokes regime we can do it, because in Stokes regime we know what to put in here, but generally for the whole equation we don't have this explicit expression between particle size and velocity, and this is basically the important question you want to solve. What is the drag force of a given size at a given velocity, or at a given velocity what is the size of the particle of interest. So now we look into one application or example why this question is important, and this is spray drying. So here you see a schematic picture of a spray dryer, not a big one in industry, but the principle is the same, but it's more a device we have in our lab for the lab class in particle technology. So a spray dryer is a device which converts a liquid feed, so we have a suspension or slurry, this is the blue arrow here, into a dry powder by rapidly drying it with hot gas, which is typically air. So what we do is we have a liquid and we dry it in hot air, and then we get very nice dry powders, and a spray dryer consists out of an atomizer, and this creates the fine droplets from the liquid. So this is what you see here. The atomizer makes, for example, with very high pressure, it presses the liquids through the nozzle, and then you create a lot of small droplets, and then we have the air heater. So air is coming in here, it's heated, and then both goes together in the drying chamber, and in the drying chamber the droplets are dried, and then the droplets follow the gas stream, so the dried droplets, so the powder follows the gas stream into a cyclone, and in the cyclone the larger particles are separated and collected here. So this is the product, this is the powder you want to have. And then finally, because you always have some very small particles which you don't want to have, and they go with the airstream out of the cyclone, and then you typically have a back filter here which collects the rest of the particles, and then you have very clean air. And what you see here is basically the droplets which are not completely dried, because sometimes you have large droplets and then they just fall down and you collect the liquid here. And this is the idea of a spray dryer, and these devices are very often used in pharmaceutical or food industry. And if we take now a look at typical values, so a very simple diagram, we have the Reynolds number here, we have the particle velocity, and this is the particle velocity of a droplet or powder in a spray dryer. And here we have typical sizes from small droplets to middle to large droplets, so 10 to 100 microns, and typical velocities, which is 0 till 10 meter per second, so there's also a larger range, but these are quite typical values. And if we calculate now the Reynolds number for these particles, you see that we have values between 0, well, not 0, but a little bit larger than 0, and something up to 50, 60. And if you remember now the regimes we had so far for explicit solution of the drag equation, we had the Stokes regime where the Reynolds number is smaller than 1, and we have a Reynolds number between 10 to the power 3 and 10 to the power 5, and there we have this Newton or quadratic regime. And the Reynolds numbers we are here are too large for Stokes, but too low for quadratic regime. So this is this in-between regime where we not really have a good solution or good equation. So for spray drying, we really have a problem that the explicit solutions we have cannot be used to calculate the drag force. And therefore we have another approach which we could use, and this is that we make the equations dimensionless. So what you see here is the settling velocity and the settling velocity of a particle, and this is not calculated for Stokes regime or quadratic regime, but this is if you make the force balance of buoyancy, gravity and drag with using the general drag equation. Okay? And then you will get this expression, and in this expression you still have CD as a function of Reynolds, so we cannot solve it. And the idea is to make this expression dimensionless. And we can do this by multiplying the full equation with velocity divided by viscosity G, density of the fluid to the power to the square, and then we have here density of the particle minus density of the fluid. And if we multiply both sides, we get this expression, so V and V squared, so V to the power 3. And then we have here, and there you have to be careful, this is the terminal velocity, and this is the kinematic viscosity, right? The dynamic viscosity and density can be both rewritten as the kinematic viscosity. Be careful because they look very very similar, right? So this is why I have the indice here, and then we have the G, and then we have just one left, right? So here we multiply with density of the fluid to the power 2, and then we have just one left because one was transformed, and then the rest we just can copy paste. And on the other hand, we just have this full part here. And if you look now at this full expression, you should recognize something. And what you recognize is this one cancels out, right? Density of the particle minus density of the fluid divided by density of the particle minus density of the fluid. So this cancels out. Then the G goes out. And then we have now a D. We have a velocity. We have density square, density, so just one density, so we have D particle size, velocity, density, and a dynamic viscosity, so we have the Reynolds number, right? So we can simplify this expression very easily. So what means is that when we cancel out and the leftover is 4 divided by 3, Reynolds number divided by CD as a function of Reynolds number. And the expression here or the expression here, both are equal, right? So this equals this equals this. And this is defined as the omega number. And the omega number is just omega here, is now a function, and now you can take a close look into this equation here. This is the omega number, similar as this is the omega number, all are the same, right? And here we have an expression where we have the velocity of the particle without the diameter. So now we have a clear, easy expression to calculate the velocity of the particle without that we need to know for this number the particle size. And the same we can do if we take again the general settling equation, and now we multiply with 3 divided by 4 because we want to switch this expression, as you will see, and then d particle size to the power 2, density of the fluid to the power 2, and viscosity to the power 2, and then Cd as a function of Reynolds. So we multiply this full expression with this term, and if we do this, we have v squared, right, velocity squared, and everything from here is on this page. And now you can see, okay, this looks like 2 Reynolds numbers, right? Velocity, diameter, density divided by viscosity, the Reynolds number, everything is squared, so Reynolds number squared. And if we look again at this part and this part here, we also can do a little bit the math. So for example, we have dp and dp squared, which is dp3. And here we have again kinematic viscosity, and then we will get the final equation, which is Reynolds number squared, 3 divided by 2, divided by 4, sorry. And here we have density of the particle minus density of the fluid divided by viscosity to the square, divided by, or multiplied by the density of the fluid, and then we have g dp to the power 3. And this expression is defined as the so-called Archimedes number. Okay? And the Archimedes number is now similar as the omega number, a number which only depends in this expression from the size of the particle. So there is no velocity of the particle. So if we only know the size, we can calculate the Archimedes number. If we only know the velocity, we can calculate the omega number. And there is a quite old publication from Grassmann and Reinhardt zur Ermittlung der Sinkgeschwindigkeit von Tropfen und der Steiggeschwindigkeit von Blasen. And what you see here is the Archimedes number over omega number. So they made this derivation and they calculate and put this into a diagram. And then you see for different Reynolds numbers, so Reynolds 10 to the power 2, 10 to the power 3, 10 to the power 1, for different Reynolds numbers, you can calculate now the, if you know the velocity, for example, you can calculate, if you know the size, you can calculate the Archimedes number till you reach the Reynolds number, and then you can read out the omega number. And when you know the omega number, you can calculate the velocity now. And here you see these dots are experiments for droplets. And you see that till Reynolds number 10 to the power 3, the experiment results perfectly match the theory, and then we have a difference here between experiment and theory, and this difference is due to the fact that at high Reynolds numbers the shape of the droplet changes and it's not a perfect sphere anymore, while the theory considers a perfect sphere. And here this jump which you see here is to full turbulence occurring, but we have a little bit nicer diagram here which is easier to work. So here is the Archimedes number, here is the omega number, and if you know the size of a particle, you can calculate the Archimedes number, and then you go to this line for a given Reynolds number, and then you can read out the omega number, and if you read out the omega number, you can reshape the equation, and then you can calculate the velocity. And the cool thing is you can do all this without knowing the flow regime. So you don't have to think if this is what you see here, Stokes, or this jump here is the intermediate regime between Stokes and quadratic. You don't need this. When you work with this diagram, you just need the size or the velocity of a particle, but you don't need the explicit depiction of the drag force. And this is the advantage here. So, some exercises to train your knowledge, which you should get from this video. So first, think about the problem of drag for Reynolds numbers larger than Reynolds numbers 1. So why this is a problem if we have a higher Reynolds number, and why we not can use our so far derived solutions. So why we need all this, then derive the Archimedes and omega number by yourself. I'm always a big fan if you rewrite the things by yourself on pen and paper. And then I would ask you to calculate the velocity of a water droplet, which has a size of 600 microns in air. So you have the size, you have the fluid, and what is now the velocity, and use the diagram I showed you in this video. And finally the other way around, so calculate the size of a water droplet falling with a velocity, a terminal velocity of 3.5 meter per second, also in air. And if you can do all these quite simple exercises, you should get the main ideas of this video. And with this I hope you could follow me for the closer look at the drag equation and which is problematic regarding to flow regimes. Then we shortly talked about spray drying and why spray drying is a nice tool and why it's also important for the point I want to make in this video, because we're in intermediate flow regimes, and then we discuss how we consider these flow regimes for particle settling by introducing the Archimedes and the omega number. And with this, I would like to thank you, and if you have any questions, just let me know.